In the last lecture, I explained about the transient analysis of RL circuit when it is excited by DC supply using differential equation approach and using Laplace transform approach. Now in this lecture, I am going to explain about the transient analysis of RC circuit when it is excited by DC supply using both approaches. Now, transient analysis of RC circuit with the differential equation approach. So let us take the RC circuit of resistance R ohms, capacitance C, supply is of Vs, current in the circuit is I, and switch S. Suppose the switch here, the assumption is initially the capacitor the charge of the capacitor is 0. It is charged to 0 volts. Now switch S is closed at t equals to 0 instant. So after closing the switch, after t greater than 0, after closing the switch, so by applying KVL for the circuit, means from the circuit we can write V minus Vs by R equals to minus C into dV by dt. Of course, we can write Vs minus V by R equals to C into dV by dt. Here I am taking V minus Vs by R equals to, so I should take negative sign, minus C into dV by dt, where, see here, where V is the voltage across the capacitor. Now from this I can write minus 1 by RC into dt equals to 1 by V minus Vs dV. Now integrating the above equation on both sides gives minus 1 by RC into integral 0 to t dt equals to integral 0 to V means V of t 1 by V minus Vs dV. So integrating the above equation gives and putting the limits 1 minus 1 by RC t minus 0 in the right side ln of V minus Vs of limits 0 to V. V means V of t. So putting the limits gives minus t by RC equals to ln of V of t minus Vs minus ln of minus Vs after putting the limits. Now it becomes right side ln of V minus Vs by minus Vs equals to ln of Vs minus V of t by Vs. Now totally the equation becomes Vs minus V of t by Vs equals to e power minus t by Rc, taking this ln to the other side. Now finally from this, if you write V of t, then it becomes V of t equals to, separating V of t, it becomes Vs into 1 minus e power minus t by Rc. If you write the charging current through capacitor, it becomes I equals to current in the circuit Vs by R into e power minus t by Rc. If you see the waveform for current, if you put t equals to 0 in the equation, it becomes current in the circuit becomes V by R. So as t is increasing, as we are approaching to infinity amount of time for after long time, if you put t equals to infinity in the current equation, the current becomes 0. That means if the capacitor is fully charged to the supply voltage, then the current will be 0, because the voltage across capacitor is V and the supply voltage is V. What will be the net current between this supply voltage V and charged voltage V? 0. So that's why the current reaches to 0. If you see the voltage across resistance and voltage across capacitance, see the voltage across resistance, initially it is of full value of supply voltage. After t approaching to infinity, the voltage across resistance becomes 0. If you see the voltage across capacitor, initially it is 0, because a capacitor acts like short circuit for a DC supply. So voltage across short circuit becomes 0, that's why initially it is 0. As t is approaching to infinity, after long time, slowly this will be charged to the supply voltage, so that the voltage across capacitor will be the total supply voltage of V after long time, means after t equals to infinity. So see the waveform, finally Vc is approaching to V, supply voltage. Theoretically, if you put t equals to infinity in the expression of V, voltage across capacitor, it will show V. Now finally V of t equals to Vs into 1 minus e power minus t by Rc. I can write that Rc as tau, it becomes Vs into 1 minus e power minus t by tau, where tau is called the time constant. So time constant for RC circuit is tau equals to Rc. So here the time constant definition means it is the time taken for the response to reach 63.2% of its final value. So 63.2% of its final value means here final value of capacitor is finally it is charging to the supply voltage V. So 63.2% of V, in order to reach this value, the time taken for the capacitor is nothing but here time constant. So or you can also define this time constant for this RC circuit as, the time constant of RC circuit is defined as a time taken by the current through the capacitance to fall to 36.7 of its initial value. So initially it will be 100%. So the time taken for the current to fall to 36.79% of its initial value. So that time is also said to be the time constant for RC circuit. Here the students can be asked a question, that is, define a time constant of a RC circuit. So what is the time constant of RC circuit? So tau equals to RC. So theoretically the statement is it is a time taken for the response. Here the response means voltage across capacitor to reach 63.2% of its final value. Now you can also be asked to give the justification for the second answer. Voltage across capacitor cannot change instantaneously. Justify this statement. So what is the reason behind that? Current flowing through capacitor is IC equals to C into dV by dt. If the voltage across capacitor changes instantaneously within a zero time, then it requires a current of infinity value. So which requires infinity amount of power. So which is not possible practically. That's why capacitor does not allow any sudden changes in voltage. Now let us see the transient analysis of RC circuit by using Laplace transform approach. So let us take an RC circuit. Current in the circuit is I, switch S is closing at t equals to 0 and Vs is the supply voltage. Here also assumption is capacitor is initially not charged and switch is closed at t equals to 0. So after closing the switch means for t greater than 0, if you apply KVL, it will be V minus Vs by R equals to minus C into dV by dt. Now, of course, you can also take that as a KCL. That means we are writing two currents. So Vs minus V by R equals to minus C into dV by dt. But here I am writing V minus Vs by R. So it becomes minus C into dV by dt. Now here Vs means supply voltage, V means voltage across capacitor. Now from that we can write V minus Vs equals to minus RC into dV by dt. So simplifying that gives applying Laplace transform. Here we are using Laplace transform approach. See here. So Laplace transform of V means what is that? V of S minus that Vs means here DC supply. So Laplace transform of constant means constant by S, Vs by S equal to right side it becomes minus RC into S into V of S minus V of 0. Here V of 0 is 0, there is no voltage across capacitor initially. So it becomes minus RC into S into V of S. Now if we take V of S common, V of S into 1 plus SRC equals to Vs by S. From this if you write V of S, then it becomes Vs by S into 1 plus SRC. If you rewrite this, Vs by RC into 1 by S into S plus 1 by RC. If you do the partial fractions, then it becomes Vs into 1 by S minus 1 by S plus 1 by RC. Now finally by applying inverse Laplace transform for this equation, which becomes, so V equals to, so doing the inverse Laplace transform, V of t equals to Vs into 1 minus e power minus t by RC. For that first term, inverse Laplace transform becomes 1. For that second part, it becomes e power minus t by RC. So finally Vs equals to V of t equals to voltage across capacitor equals to supply voltage Vs into 1 minus e power minus t by RC. If you draw the voltage across capacitor and voltage across resistor, here also see the equation of voltage across capacitor. If you put t equals to 0, so the voltage across capacitor will be 0. If you put t equals to infinity, it will be V. So theoretical analysis, in the analytical point of view also, initial capacitor acts like short circuit. That's why voltage across capacitor is 0. So Vc is 0. So finally it will act like open circuit. That means total supply voltage will be appearing across capacitor. So that's why Vc equals to V. So in the same way, initially VR means total supply voltage appears across resistor. That's why VR equals to V. So finally the total supply voltage will be appearing across capacitor. That's why so VR becomes 0. Now if you see the current in the circuit, I equals to V by R into e power minus t by RC. So from that I can draw this curve. Initially for t equals to 0, current is V by R. If you put t equals to infinity over there, the current becomes reduced to 0. Because in the final instant capacitor is fully charged, so there will be no charging current, because already it is fully charged, so charging current will be 0. That's why current is 0. So let us take an example. Find the current in the circuit shown in figure at an instant t after opening this switch at switch S. If a current of 1 ampere had been passing through the circuit at the instant of opening. So initial current is taken as 1 ampere. See the circuit. Now the solution is, So let us apply KVL. After opening this switch, it becomes 6 into I of t plus 5 into di of t by dt equals to 12 plus 24. See here. So it is 12 plus 24, 6 into I of t plus 5 into di by dt. Applying KVL, switch is open. Now, so taking the Laplace transform on both sides, which gives 6 into I of s plus 5 into s into I of s minus I of 0 equals to 36 by s. Now simplifying the above equation gives where initial current is given as I of 0 equals to 1 ampere, putting that value and taking the I of s common, which becomes I of s equals to 6 plus 5s equals to 36 by s plus 5. Now finally I of s becomes 36 plus 5s by s into 6 plus 5s. Now further simplification of gives after doing the partial fractions, I of s equals to 6 by s minus 5 by s plus 6 by 5. Now taking the inverse Laplace transform of above equation gives I of t equals to 6 minus 5 into e power minus 6 by 5 into t. So now let us see one more question. If the switch is closed at t equals to 0, what is the current in the circuit? See the circuit, it is having 100 volts DC supply. Through switch, it is connected to capacitance of 10 farads and resistance of 10 ohms. So what will be the current when the switch S is closed at t equals to 0? Now options are given. A equals to 0 amperes for option B, 10 amperes for option C, 20 amperes for option D, infinity. Please answer this question. Now the answer is, so current in the circuit is 10 amperes. So after closing the switch, because the capacitor acts like short circuit, now the current in the circuit becomes 100. This supply voltage 100 by that resistance 10 ohms. So answer is 10 amperes. Thank you.